Hello, good morning everyone. So today we are starting again, just like we said in our last presentation. We shall be looking today at symmetries of the Riemann tensor. So like we obtained last time, we obtained something of this kind last time in our presentation. Not a kind of a derivation anyway, but it was something that we used in such a way as defining the Riemann tensor, of course, from some commutator. And of course, if we want to find the completely covariant Riemann tensor, this is what we will need to do by sort of contracting that sigma here with a metric tensor, and that is what we get. Of course, we also know that the completely covariant Christoffel symbol is given by this. And like we have said before, the usual cyclicity, you take this as one of the commutation. Next you have mu, comma, lambda, and the rest follows. Of course, also, if we do want to define this mixed kind of Christoffel symbol, all we need to do is to perform a kind of a contraction, some kind of contraction like this. So, for instance, in the case we have just written, we could have, for instance, when we have a tensor, say the Christoffel symbol, sorry, not a tensor actually, because Christoffel symbol is not a tensor. So, if we have a Christoffel symbol, say of this kind, and this of this kind, this of course could be obtained from the completely covariant forms of this. Now what we want to do is to rewrite the Riemann tensor in the form that is manageable, such that we can bring out the symmetries of the Riemann tensor like we intend to do. So looking at this, for instance, we want to substitute this Christoffel symbol in the Riemann tensor with the hope of reducing it to the nearest minimum, if possible, maybe even do away with the Christoffel symbol entirely, but as it turns out, we may not be able to do that. Anyway, but going through this, for instance, represented by this object, differentiating this with respect to sk, just by the usual Leibniz rule, we treat this as a constant, and then differentiate this, then plus. We keep this a constant, differentiate the second part. The same, of course, is applicable for this one, differentiating with respect to x nu. As you can see here, we will eventually have to find the difference between these two. So we're just trying to make everything as elegant as possible. So the difference between these two is what we have written out here, whereby all the terms this plus that minus that. However, we stated that the completely covariant Riemann tensor is given by such a contraction as this. So we will have to multiply, because if you remember, the difference that we have here that we've written here is what is actually contained in this Riemann tensor as defined by this one. So the completely covariant Riemann tensor will be given by this metric tensor multiplying across the whole Riemann tensor that we have originally. So as you can see, G sub lambda sigma multiplying across the whole tensor. And of course we have found the difference between these two, and so we're just going to multiply through with the metric tensor through the whole Riemann tensor. The last term here is what we have here, and of course every other messy term that have occurred before this point is the difference that we have obtained along this line. Okay, now so something that would be useful for us is the definition of this conical delta using these two metric tensors. Differentiating both sides, this being a constant will give us 0. By Leibniz rule, we are going to have that when you treat one a constant differentiating the other, you will have something of this nature, this being equal to minus that. So it's just like bringing this to the back of this and this to the other side, but then you get a minus sign. Remembering also from our last presentation, we have shown that this was equal to that, and of course from which we were also able to show that the covariant derivative of the metric tensor is equal to 0. Yeah, of course, then when we had to find the covariant derivative of a metric tensor, remembering that these are two covariant indices, we had gammas with minuses, which eventually cancelled these terms and gave us 0 for the covariant derivative of the metric tensor. Anyways, but we're just applying this definition. Now, given the fact that we have this to be equal to minus that, we can see that this being equal to minus this, we have this as a whole. So what we intend to do here is to replace this whole derivative with this entire thing here. That's what we've done. And so similarly also, this also is equal to that, and that gives us that. Of course, you can see why we need to do this is because here in the difference, or in the Riemann tensor, we have G sub lambda, the G rho sigma, the SK. So as carefully selected, we can see that this particular factor here has been rewritten as that. And the same also applies for this one here. Yeah, exactly. Of course, we're not looking at the sign for now. So this also has been rewritten as that. So, and that is the essence and the need for us to have putted this result. Now, looking up further. Okay, so you will have to maybe pause in the previous slide to be able to see the following substitution. In the factor, we talked about how we made the changes. We have substituted it here for the first factor, and also here for the second one. And now looking at the previous slide, you can see that we had the products of two metric tensors here. And for each of them, we have been able to convert to conical symbols or conical tensors. Of course, you can check those metric tensors and see that anytime you have such a product, you end up with this kind of conical tensors. Now, looking further at this factor, this combination, you can see that this looks like G rho sigma with this totally covariant Christoffel symbol with gamma mu nu rho, which is equal to that. Now, the same, of course, is true of that, and plus this term here, and these other two terms coming from the very last expression we had just before this part. Now, moving on, of course, we just had to use the conical deltas that we have obtained here and here, making sure we evaluated it. Now, looking at this, for instance, it means here that every lambda will change to rho, or depending on what we do. Okay, now we actually chose every rho changing to lambda. So that's what we've got, every rho changing to lambda, and that is what we have. Here also, I guess we changed every alpha to lambda, so and that's what we've done also, all through in this case. Now, the first two terms over there, this term, of course, just keeps following us. So for now, we just keep it to tag along. Now, looking at this particular expression here, this whole factor which we said is equal to that, you can see this first term is simply multiplied by, yeah, exactly, simply multiplied here by this conical delta. So this actually multiplied in, so the gamma eta kappa lambda is multiplied by gamma sigma mu nu, and then the gamma eta kappa sigma is multiplied again by gamma sigma mu nu. And all of them, of course, along the line have been multiplied respectively by the metric tensor G sub eta sigma, G sub eta lambda. Now the same is applicable here also. Now, of course, this is the same as we can see as gamma here. I have here to be sigma mu k. So that gamma sigma mu k, gamma sigma mu k, gamma sigma mu k multiplies that. In this particular term here, we simply just opened up the bracket, and that's what we have. So this is the metric tensor G lambda sigma multiplying through this minus that. And of course, in the last expression, last two expressions, you can see here we have used comma to denote partial derivatives. Now, for each of these being differentiated either by x kappa, x nu, we have double partial derivatives. So that's why we have comma mu k, comma lambda k, comma lambda k. Yeah, exactly. So I'm sorry, I think there was a mix-up here. We're going to figure it out. It's all good, everything is nice. So this actually here in this case was comma nu k, not lambda. So that was simply just repeated. Comma nu k. And then, okay, in the same case here also, we have comma mu, comma lambda. So you can see comma mu k, comma k nu, comma lambda mu. So in each of these also, we have a following expression whereby we have this followed by, so this also has to be nu because it's a partial derivative, second order partial derivative because of this. Now in this, we're able to make some identification. We can see here that terms which are of similar labelings are the same except for a sign, a change in sign. For instance, this is labeled 1. Now we can find another term here which is labeled 1. These two terms are essentially the same except for the difference in sign. The same in the sense that we have this double dummy index sigma sigma. Here in this case, we also have eta eta. Down here we have exactly mu nu and sigma. Here we have exactly mu nu, but this eta is one of the dummy indices. just like the sigma here is one of the dummy indices. Now we have following here to be G lambda sigma. The sigma, of course, happens to be this, and then the lambda occurring nowhere else. Now sigma, just like here also, we have eta being repeated here, and lambda again occurring nowhere. So in other words, these two terms are the same, so these two terms will essentially cancel. Now also we have here this one label 2 and this label 2. Now we have just the same kind of situation here. Eta repeated, and then you also have sigma repeated. And here we have here nu multiplying that dummy index. Nu also multiplying the dummy index. And so in the metric tensor also we have G lambda sigma. Sigma is not repeated anywhere. We have G lambda eta. Eta is not repeated anywhere. So again, these two terms cancel. Now what we are left with is a combination. Okay, so in this double partial derivatives also, now just like we rightly corrected in some of these indices, you can see this is comma k nu, this is comma nu k, of course it's the same, partial derivatives, ordinary partial derivatives commute. And this is G lambda nu, and both are labeled 3. They are all the same, of course, you have a minus sign here, except for a difference in sign. So these two cancel. Now all that we are left with is what we've combined here. In the first term, we've combined the terms that have gammas. So we have this one minusing that. And of course, we can see that exactly the same metric tensors follow. G eta sigma here. Now plus whatever is left of our second order partial derivatives, this very first one here, which has nothing to cancel it. And then this one here with a minus, and then this two with a minus, and obviously this last one here with a plus. That is what we have left there. And this is the form we will need the Riemann tensor to be in, or at least at this stage, we can try to observe some of the similarity properties or symmetric properties that we intend to study. Now, one of the symmetric properties we intend to study is letting lambda become nu and nu becoming lambda. And here we are letting, so the idea here is we are letting lambda becoming nu and nu becoming lambda. Here we are letting nu become kappa and kappa becoming mu. In other words, in essence, when you look at this Riemann tensor, what we have done actually is to interchange, bring nu k in front and take lambda nu in that order to become just taking them to the back. And that's what we have over there. That's just the transformation we have made. In other words, we are going to perform this transformation on this expression on the right hand side in this form of the Riemann tensor. So wherever we see lambda, we just change it to nu. Like in this case now, this is lambda, we've changed that to nu. And wherever we see mu, we change it to k, and k becomes mu. And of course, that's what we have done in this case. Now the same thing goes for all the rest of the terms there of factors. And that's what we've done. But then you realize that in the end, all we have done for the first cases, but in these cases, we have simply just placed one in front of the other, especially, now you can see I have here gamma, sigma, k, mu. And this is symmetric with respect to the interchange of the lower indices for the Christoffel symbol. Now as you can see, because of that, it's just the same. Here I have nu lambda, but I guess here I have lambda nu. That is again the same. Minus. So by the time you look at this, you can see it's just an interchange in terms of the Christoffel symbols. Now here also we've had just the same thing. It's just an interchange, as you can see, of the partial derivatives which all commute. So in the end, we can see that by the time we perform this transformation from this to this, that is taking these two indices, bringing them to the front, and the first two taking them to the back in that order, essentially gives us back what we had before as the Riemann tensor. So this is our symmetry property number one. That is, that whenever you perform this transformation, you get the same Riemann tensor, so nothing changes. Very quickly, we'll be looking at the next symmetry property. And the next symmetry property is interchanging mu with lambda in this case. Now here, this is what it means. Whenever we see mu, we change it to lambda. Whenever we see lambda, we change it to mu. So in other words, we're just changing this particular Riemann tensor to something like this, whereby we bring mu in place of lambda and lambda in place of mu, leaving the last two indices untouched. Now, if we did that, it's just like we have said before, coming down here, so we can just look at one term. For instance, this is the last term here. So let's look at it. We have here in this expression a mu. So we intend to change this mu to lambda. As you can see, that's what we've done here. And here we also have, so where do we have a lambda? So we have a lambda here also. And we intend to change this lambda to a k. To a mu, sorry, and you can see that is what we have. So you can just perform the same operation on this same Riemann tensor by replacing lambda with mu wherever you see lambda, and replacing mu with lambda wherever you see mu. Performing that expression, this is what you get. But then, of course, we realize something here. We can see in this case that the very first term, gamma eta mu lambda, gamma sigma mu kappa, that these two expressions, this particular one which actually occurred here first, has become changed. As you can see, this gamma nu mu, and then lambda kappa, or well, in this case, this is what we've got. This is lambda, please. I'm sure I've always had my eta and lambda mixed up. So this is lambda kappa. You can see that this becomes the first term. This particular term here, as you can see, with kappa mu lambda was actually our first term here. Kappa mu lambda was our first term. So you can see an interchange. Now the same also applies to all the terms here. You will realize in the end, for instance, this is g mu comma lambda k. So you can look for g mu. So g mu, or you can say mu, this is all the same, comma lambda k. This is what I have here. It has a minus sign here, but here it has a plus sign. So apparently the same thing is true for every other term here. You realize that each and every one of these has just been sort of replaced. In other words, if I pull out a minus sign from this expression, I'm going to have minus, and everything here in the parentheses looks just exactly like what we had initially as our expression over here for the Riemann tensor. So what we've got is minus entirely the Riemann tensor. So what we've shown actually is that whenever you perform that such a transformation as just direct displacement, that is, for the first two indices, you displace them in this form, or you can just say permute them such that mu comes to the front and lambda goes back, you produce a minus sign. Now the same is true apparently also for the last two indices. If you leave the first two indices untouched and change the last two indices, you get a minus sign. If you perform the two operations all at the same time, of course you get a plus sign. And this is our symmetry property number 2. Now the next symmetry property here is a sort of cyclic permutation. In this case, what we intend to do is, for instance, is to say that every mu changes to kappa. So let us look at this way. We have our Riemann tensor R here, lambda mu kappa. In other words here, what we're saying is we are intentionally leaving the first index untouched, that's lambda. But we're changing every mu to kappa. So we're sort of changing every mu to kappa, and we're changing every nu to mu. And then we're changing every kappa to nu. Sort of. So it's a kind of cyclic permutation. Now we just kind of, so what we intend to do in this first case is to change this Riemann tensor for an expression like this, leaving the lambda untouched. You can see now what we have done is to have pulled in this expression. We sort of pushed it forward like this, bringing in kappa in front, and then having mu in that order. So if we perform this transformation on this expression, that is, like we said, making every mu. For instance, here we have a nu. So let's just look at the nu. What did we say about the nu? Change the nu to mu. So you can see that our nu here becomes a mu. And you can see that for every nu here, which was the very first one here, we change it to, of course, okay, we've said that already. For every mu, let me just go straight. For every k or kappa, change it to a nu. So let's look for this is a kappa. Now we intend to change it to a nu, and that's what we have here. Repeat the same thing all across the expression. And what you're going to obtain is this. At this point, of course, we have nothing obvious to say about that. And next also is just repeating the same kind of expression. So, in other words, we are trying to again perform a transformation that continues from here, if you like. Of course, we are going to start from the Riemann tensor expression just like we had here. But what we intend to do now is to perform such an expression as this, mu being changed to nu, mu changed to kappa, and kappa changed to mu. The whole idea is that the whole Riemann tensor that we had originally becomes this, nu k mu. But of course, you can see that this could have as well have followed from this one. That is, by simply just performing a cyclic permutation, whereby again leaving the, the lambda untouched, we simply bring the nu here in front, with kappa following suit and mu being the last. Now, if we perform that transformation, all you have to do again is carefully take your time, change here every mu to nu, and every nu to kappa, and every kappa to mu, and I assure you, hopefully this is just what you're going to get. Now we're writing the original Riemann tensor that we've obtained here, all over again here. Now we've noticed something in this expression. Again, every such term that is having that have similar labels, either 1, 1, 2, 2, are all the same again, of course, except for a difference in sign. And we're doing this because it's going to be far more convenient for us to be able to cancel. Now you can see in this combination, I have 1 here, tilde on top of it, and this is the same thing with this. In fact, in this case, is exactly in all the indices. You have, okay, a set of course interchange, which is still the same, mu kappa here, kappa mu, the same of course for the Christopher symbol. But then I have the sigma, sigma here, nu lambda, eta, g sub, eta sigma, g sub, eta sigma. So they all have the same label. Of course, it's a plus here, but it's a minus here. Now I have a tree here labeling this, and this is also a tree. Now this is the same exactly, in fact, again, except for this displacement, which is inconsequential. You have nu kappa here and kappa nu. So these two are the same. In other words, this cancels this because of the difference in sign. This cancels this. Please take your time in doing this. You'll find this is fun, and actually this is all true. Being careful with the ordering of the indices. Again, this is label 2, and again is our belief that this 2 here has another 2, of course, which should be the same with that. And so this again cancels that. And now we have here with us a 4. So this is a 4 here, cancelling this. So you can see a minus sign here, but a plus sign here. Everything is the same. Nu lambda, comma k mu, but here comma mu k, which of course is the same. Double partial derivatives. Now the same thing happens here also. If I'm looking here at g sub, 5, I just need to look for a 5 here very carefully. Again, we're certain it should be somewhere here, and that is it. This again cancels that. And then we have a 6 here, taking it in that order. This is a 6, and it cancels that. Take note, this is a minus and this is a plus. So the cancellation is all valid. Now again, we're expecting that for a 9, okay, well, we can jump to, okay, well, we have a 7 here. And this is a 7, plus, minus. So this 7 cancels this 7. And where else again? We have an 8 here. An 8 here also combined with some other 8, which I'm sure should be there. This cancels that. And then finally the 9s cancel again. All the difference. So if you look at this whole thing, all the terms are gone. Sorry, when I was saying cancellation, I had the intention of adding up these whole expressions or equations. And as you can see, when you add them all up, you get 0. So leaving the first indices untouched, the first index untouched, lambda where it is, and you just go by some cyclic permutation, you have mu coming, okay, well, whatever, but you can see it's all the same. So maybe if I'm to start from here, mu coming to the front, that is mu, I have mu, kappa following suit. I perform the same operation, kappa coming over, mu, and then nu all over again. The summation of all this gives you 0. And this is our symmetry property number 3. As we go further, of course, we tend to look next at the Bianchi identity and some other properties that come from this. So as we move on, we hope that you join us in the next presentation, where we shall be looking at other symmetry properties of the Riemann tensor.